Welcome everyone to another deep dive. Today we're embarking on a mission.
A pretty massive mission, really.
Yeah, exactly. We're exploring a hidden foundational shift that is happening silently underneath the entire internet. We are talking about the global transition to IPv6.
Right. And I know what some of you are thinking.
Yeah, if the phrase networking protocols makes you think of some like dry IT manual best left in a dusty server room, stick around.
Please do.
Because this is actually about the future of how every single object in your life is going to connect, communicate, and just generally function.
It's the digital fabric of the world we're building.
It really is.
Yeah.
And our deep dive today is based entirely on excerpts from Silvia Hagen's really comprehensive book, IPv6 Essentials.
It's a fantastic resource.
We are taking her research and unpacking what it means for the very architecture of our digital lives.
And Hagen's text is honestly an essential roadmap for this topic. The transition to IPv6 is frequently pitched to the public, merely as a way to create more room on the internet.
Like adding lanes to a highway.
Exactly. But treating it just as a larger address space fundamentally misunderstands the scope of the project. We're looking at a complete architectural upgrade of the internet itself.
A total teardown and rebuild.
Yeah, because the current infrastructure is based on a system designed in the 1970s for a closed circle of researchers.
Right.
And we're moving to a framework engineered to support billions of humans and trillions of interconnected devices natively without all the duct tape solutions we rely on today.
Okay, let's unpack this. Because to understand the destination, we really need to look at the origins of what network engineers call the IPv4 crisis.
The crisis, yeah.
Looking at the timeline Hagen provides, how is it even possible that a protocol designed decades ago hasn't completely collapsed under the weight of the modern internet?
Well, to map out that crisis, the text points us to Hobbes's internet timeline.
Which is a great name.
It is, and it's a fantastic historical record. If we trace the roots back to 1969, we see Steve Crocker publishing the very first request for comments. Right, RFC1, titled Host Software. And RFCs are essentially the official rulebooks and standardization documents of the internet.
The blueprints.
Exactly. Now, back during the dawn of the ARPANET, the network ran on the Network Control Protocol, or NCP.
Okay.
By 1971, the entire network consisted of exactly 23 connected hosts.
23.
That's it.
I mean, I have more than 23 devices connected to the Wi-Fi router in my living room right now.
We all do.
It really puts into perspective how localized that initial concept was.
It was tiny. The initial design fundamentally assumed a closed, highly trusted environment. But the major pivot happened on January 1st, 1983.
Flag Day.
Yeah, a massive coordinated cutover was executed, moving the network from NCP to the TCP/IP protocol suite.
And that suite included Internet Protocol version 4.
IPv4, right. The architecture held steady, but then in 1991, Tim Berners-Lee introduces the World Wide Web.
And everything changes.
Overnight, suddenly the internet transitioned from a specialized academic tool into a public commercial juggernaut.
But underneath that massive public expansion, the core engine remained IPv4.
A protocol that utilizes a 32-bit address space.
So, doing the binary math on a 32-bit space gives a theoretical maximum of about 4.3 billion unique addresses.
It sounds like a lot.
Right. I mean, in the 1970s and 80s, when computers were massive mainframes and the global population was significantly smaller, 4 billion probably sounded indistinguishable from infinity.
It absolutely did. The assumption of inexhaustibility was woven into the very way those addresses were initially distributed.
Like they were handing out candy.
Because the problem today isn't just the hard limit of 4.3 billion, it is the historical legacy of geographical disparity.
Who got what and when?
Because the internet was born in the United States, early allocation methods were based on a classful networking system that handed out massive blocks of addresses with zero anticipation of global scarcity.
Right, the Class A blocks.
Major U.S. corporations, universities, and government agencies were assigned Class A blocks, and a single Class A block contains over 16 million IP addresses. So these entities were sitting on millions of addresses they could never realistically use, while the global registry was depleting.
Just hoarding them, essentially.
Unintentionally, but yes.
Yes.
As a direct result of this historical artifact, the United States, representing roughly 5% of the global population, ended up holding about 60% of all allocated IPv4 addresses.
That is wild. That leaves the remaining 95% of the world fighting over 40% of the address space.
A massive bottleneck.
The book notes that regions like Asia, which were experiencing massive technological and population booms, found themselves completely starved for fundamental networking resources.
The disparity created a hard ceiling on technological deployment in those regions. They simply lack the raw IPv4 resources to provide baseline internet access to their population.
Let alone scale up new infrastructures.
Exactly. And that scarcity is compounded exponentially by the second major driver of this crisis.
The device explosion.
We have completely moved past the era where the only thing needing an IP address was a desktop power on a desk.
Oh, for sure. The examples in Hagen's text regarding this device explosion are wild. It mentions early internet-capable gaming consoles like the Sony PlayStation and Nintendo DS.
Game changers at the time.
And the early ways of smart cell phones.
Mm-hmm.
But then it pivots into consumer appliances.
The smart home era.
The book literally discusses networked refrigerators, stoves, water heaters, and this is the one that really got me: networked bathtubs.
Yes.
A bathtub with an IP stack. Why?
It highlights a shift in manufacturing philosophy, integrating telemetry, power management, remote diagnostics, and automated control systems. All of that requires network connectivity.
So they're just jamming computers into everything.
Manufacturers are embedding IT stacks into virtually everything with a power source. When you examine a modern networked vehicle, you aren't looking at a single node.
Right. It's not just one IP address for the car.
You are looking at a mobile network that might require dozens of distinct IP addresses for its internal environmental sensors, navigation arrays, entertainment consoles, autonomous driving telemetry.
So 4.3 billion addresses cannot even cover the human population.
Not even close.
But becomes statistically microscopic when you factor in a global ecosystem of ambient connected hardware.
Exactly.
So if the math is that severely unbalanced, and we have billions of people and even more devices needing connections, there has to be a mechanism that kept the internet functioning.
There was a patch?
How did the IPv4 architecture survive the late 90s and early 2000s without a catastrophic failure?
The internet remained functional due to a highly effective yet architecturally destructive short-term patch introduced in 1994.
A patch from 1994 that we're still using.
Defined in RFC 1631, it is called Network Address Translation, or NAT.
NAT.
The core function of NAT is to take a single public, globally routable IPv4 address, or a very small pool of them, and use it as a massive front for an entire network of private, internal IP addresses.
I always think of NAT like a receptionist handling communications for a massive corporate office building.
That's a good way to look at it.
Inside the building, you have hundreds of employees, and each one has a private internal extension number. But to the outside world, the company only advertises one main public telephone number.
Right.
When an employee makes an outbound call, the receptionist intercepts it, dials out using the public number, and meticulously logs who made the call.
The state table.
Yeah. And when the outside party replies, the receptionist checks that log, identifies the internal extension, and routes the communication back to the specific employee.
That analogy maps perfectly to the technical reality, but we need to elevate it to see the strain it causes on the network.
How so?
At a protocol level, that receptionist is your NAT router. It is actively intercepting outbound packets and rewriting the source IP address and the TCP or UDP source port on every single transmission.
It's opening the mail, basically.
It maintains a massive dynamic state table in its memory to track these changes. When the return packet arrives from the web server, the router consults its state table, rewrites the destination IP and port back to the private internal address, and forwards it.
That sounds exhausting for the hardware.
It is an incredibly intensive process of constant packet manipulation.
It fundamentally changes the router from a simple traffic director into a bottleneck that has to open, modify, and repackage every single piece of mail passing through it.
What's fascinating here is that NAT completely fractures the original foundational design of the internet.
The end-to-end model.
Exactly. The internet was engineered on an end-to-end model. The assumption was that every node had a globally unique, publicly routable address, allowing any device to establish a direct, unmediated connection with any other device.
And NAT destroys that transparency.
Completely. And beyond the philosophical architectural break, NAT creates severe, tangible headaches for complex network operations. Because NAT modifies the IP header in transit, it breaks any application or protocol that relies on end-to-end integrity.
The book mentions peer-to-peer applications struggling with this.
Oh, massively.
Things like voice over IP or online gaming, where two users are both trapped behind their own receptionists with no direct way to establish a pure connection.
Those applications require complex, clunky workarounds called application layer gateways just to figure out how to traverse the NAT.
More duct tape.
But the most critical casualty of NAT is IPsec,
The security protocol.
the protocol suite used for encrypting and securing IP communications. IPsec utilizes an authentication header, or AH, which mathematically hashes the immutable fields of the IP header, including the source IP address.
To make sure it hasn't been tampered with.
Right, to ensure the packet wasn't altered in transit. When a packet leaves a private network, the NAT router intercepts it and changes the source IP address.
Oh, I see where this is going.
When that packet reaches its destination, the receiving IPsec gateway runs the mathematical hash, sees that the source address no longer matches the cryptographic signature, assumes the packet was subjected to a man-in-the-middle attack, and instantly drops it.
Because NAT literally is a man in the middle.
NAT fundamentally breaks native IP security.
So to deploy secure communications, network engineers are forced to build incredibly fragile, nested tunnels to hide the IPsec traffic from the NAT routers.
It's a nightmare.
And the text notes, it gets even worse in the corporate world when you deal with mergers.
Corporate environments universally rely on the same private address spaces designated by RFC 1918.
Like the 10-dot network.
Typically the 10-dot network or the 192.168 block. When two large corporations merge, you suddenly have two completely separate networks utilizing the exact same internal IP addresses.
A catastrophic overlap.
The newly merged entity is forced to either execute a massive, prohibitively expensive project to completely re-IP one of the companies,
Which nobody wants to do.
or deploy nightmare scenarios of complex double NAT mapping schemes just so an employee in one building can send a localized email to an employee in the other.
And IPv6 just fixes this.
IPv6 renders all of this obsolete. By providing massive globally unique address space, IPv6 restores the true end-to-end model and eliminates the concept of NAT entirely.
Given that IPv6 solves the NAT nightmare, the IPsec failures, and provides enough space for the IoT explosion, there is still this pervasive myth that IPv6 is an experimental, risky technology.
People are afraid of it.
There's a fear of a flag day, a mandated Friday night, where the world turns off IPv4 and crosses its fingers that IPv6 boots up on Monday morning.
Hagen's text directly dismantles that misconception. The core suite of IPv6 protocols achieved IETF draft standard status all the way back in August 1998.
1998.
It is a mature, battle-tested architecture that has been baked into routing hardware and major operating systems for decades.
So the Flag Day fear is totally unfounded.
Furthermore, the protocol designers specifically engineered transition mechanisms to explicitly avoid a flag day. The architecture allows for peaceful, prolonged coexistence.
You can run both.
Networks can run dual stack, processing both IPv4 and IPv6 traffic simultaneously on the same interfaces, or they can utilize tunneling to pass one protocol through the other. It is an organic, gradual migration.
Looking at the global adoption landscape presented in the text, it becomes obvious that the future is already here. It's just unevenly distributed based on necessity.
That's a great way to put it.
Asia emerged as the undisputed global pioneer in IPv6 deployment.
Their lack of historical IPv4 allocations forced their hand. They simply could not scale their economies without a new foundation.
They didn't have the luxury of waiting.
Japan took aggressive early action, publishing the E-Japan Priority Policy Program in 2001, explicitly outlining the construction of the world's largest IPv6 infrastructure.
And they built a showroom.
They established a dedicated IPv6 showroom to physically demonstrate the capabilities of this new architecture to vendors and the public.
The devices featured in that showroom feel like a glimpse into a parallel tech timeline.
It was incredibly futuristic.
The book highlights a Toshiba refrigerator and microwave oven equipped with built-in routing protocols and native IPv6 support, manageable via direct web access without complex port forwarding.
The Sanyo demonstrations were equally forward-thinking. They featured IPv6-capable digital cameras designed to bypass local computer storage entirely,
Just direct to the web.
instantly uploading high-resolution media directly to a home gateway from any public wireless access point. They also showcased an IPv6 television that allowed synchronized interactive media consumption across multiple disparate geographic locations simultaneously.
In 2001,
Yes.
Canon was displaying webcams capable of secure remote control over the global internet without NAT traversal configurations.
Seamless security.
And Nokia, partnering with NTT Communications, demonstrated mobile terminals fusing wireless connectivity, RFID, and mobile IPv6 to deliver authenticated, highly secure services directly to handheld devices.
While Japan was prototyping, China was executing massive infrastructural deployments.
The scale in China is always staggering.
In 2001, they initiated the China Next Generation Internet, or CNGI, project. This wasn't a small-scale test. It involved deploying an expansive IPv6 backbone connecting hundreds of university campuses, research institutes, and enterprise networks.
A massive rollout.
By integrating major telecom operators and technology manufacturers like Lenovo, China aggressively embedded IPv6 into its military communications, intelligence architecture, and consumer networking hardware. It was a holistic state-level upgrade of their digital foundation.
Meanwhile, the text notes that Europe focused heavily on leveraging IPv6 for advanced mobility and voice-over IP applications.
Right.
There's a brilliant example of a prototype networked vehicle co-developed by Renault and Cisco. This wasn't just a car with a cell connection.
No, it was much more than that.
The vehicle housed an entire internal IPv6 network managed by a built-in Cisco router.
The technical achievement of that vehicle relied on a protocol called Mobile IPv6, or MIPv6.
How does that differ from regular mobile data?
In the legacy IPv4 world, if your device moves from a Wi-Fi network to a cellular network, its IP address changes.
You drop the connection.
When the IP address changes, every active TCP session, like a video stream or a secure database connection, is instantly severed and has to be reestablished.
The buffering we all know and hate.
Mobile IPv6 solves this by assigning the device a permanent home address. When the vehicle drives out of range of a city Wi-Fi grid and connects to a cellular tower, it acquires a temporary care of address from the new network.
Okay, a temporary address.
It then seamlessly updates its home agent, a router, on its home network with this new location.
So the data is always routed to the permanent home address, and the network transparently tunnels it to wherever the car happens to be at that exact second.
Exactly.
The passengers inside the Renault are streaming video, the car's telemetry is pulling real-time traffic data, and the physical handoff between massive infrastructure networks happens completely invisibly.
Without a single dropped packet. Replicating that kind of seamless, continuous session mobility across different network physical layers is practically impossible to achieve efficiently or at scale using IPv4 and NAT.
The overhead is just too high.
The architectural overhead is too heavy.
So Asia was driven by address starvation, Europe by advanced mobility features. What about the United States?
The U.S. lagged
Because they were sitting on that massive stockpile of 60% of the world's IPv4 addresses.
They didn't feel the immediate operational pain.
That's something pushed them.
The catalyst for the United States, as documented by Hagen, was a sweeping mandate issued in 2003 by the U.S. Department of Defense.
The DoD.
The DoD announced a comprehensive directive requiring all of their networks, systems, and applications to be capable of operating on an IPv6 architecture by 2008.
When an entity with an IT procurement budget of roughly $30 billion issues a mandate, the entire global technology sector pivots.
They pivot hard. The DoD wasn't upgrading just for the sake of modernization. Modern military doctrine relies on net-centric warfare.
They needed the specific features.
They needed the ability to deploy massive ad hoc battlefield sensor grids, connect thousands of mobile units, and secure every single node with end-to-end IPsec encryption without the latency or breakage introduced by NAT.
IPv4 just couldn't handle the battlefield.
IPv4 simply could not meet the operational requirements of a modern digital battlefield. This mandate forced every major vendor, if they wanted to retain government contracts, to aggressively integrate full IPv6 support into their hardware and software.
It's a huge market driver.
It also led to the creation of Moon6, a massive collaborative effort between the DoD, industry leaders, and academic institutions to build the world's largest IPv6 testing environment, ensuring rigorous interoperability across different vendor equipment.
It's a fascinating geopolitical and technological landscape. But for you, listening to this deep dive right now, if your local IPv4 network is still sending emails and streaming video, why should you care?
The danger of remaining entrenched in IPv4 is isolation.
Being left behind.
As global infrastructure, particularly in vast markets like Asia, continues to scale natively on IPv6, legacy networks will increasingly find themselves walled off or reliant on sluggish, complex translation gateways to interact with the modern internet.
You'll be the one using the clunky translator.
More importantly, the next generation of digital innovation, massive-scale IoT deployments, seamless global roaming, ultra-low latency peer-to-peer applications are being engineered with the assumption of end-to-end IPv6 connectivity.
Because that's the new baseline.
Ignoring the transition means locking yourself out of the future capabilities of the internet.
Let's shift from the global landscape to the actual mechanics.
Yeah.
I was looking at the diagrams of the packet headers in Hagen's book, and the visual difference is striking.
Night and day.
We need to look under the hood at the IPv6 header, because it isn't just a larger version of IPv4, it is a profound redesign.
A total streamlining.
The IPv4 header was this clunky variable length structure that could range anywhere from 20 to 60 bytes, depending on what options were stuffed into it.
And variable length is the enemy of high-speed routing hardware.
Right.
A core internet router is processing millions of packets every single second. In IPv4, the router has to read the internet header length, or IHL, field just to figure out where the header stops and the actual data payload begins.
It has to do math before it even routes it.
This introduces a mandatory processing pause. It forces the router to spend computational cycles examining variable options before it can even make a decision about where to send the packet.
That sounds incredibly inefficient.
The designers of IPv6 recognize this massive inefficiency. They engineered the IPv6 header to be a fixed, streamlined, incredibly predictable 40 bytes.
Always 40 bytes.
Always. The router instantly knows exactly how large the header is, allowing it to process the routing logic in hardware via fast path switching, rather than relying on slower software processing.
To achieve that fixed 40-byte size, the designers were ruthless.
They brought a scalpel.
Comparing the two diagrams, it looks like they violently cut 5 specific fields out of the IPv4 header entirely. I noticed the missing fields are header length, identification, flags, fragment offset, and header checksum.
They gutted it.
Why gut the architecture so aggressively?
Let's analyze the removal systematically. The elimination of the header length field is the most intuitive.
Because it's a fixed size now.
Exactly. If the architectural rule mandates that the primary header is always exactly 40 bytes, you no longer require a field to announce its size. It is redundant.
Makes sense.
But the removal of the next 3 fields, identification, flags, and fragment offset, represents a monumental shift in how the internet handles data.
How so?
Those 3 fields were exclusively dedicated to managing router fragmentation.
Fragmentation. I picture legacy router fragmentation like a deeply inefficient post office.
Okay, let's hear it.
Imagine you bring a massive shipping box to the counter. Instead of the postal worker telling you the box is too large for their delivery trucks, they pull out a box cutter, slice your item into a dozen smaller pieces, shove them into smaller boxes, write complex tracking numbers on each one, and mail them individually.
And then the receiver.
Then the person receiving the package has to sit on their porch with glue, hoping all the pieces arrive in the right order so they can reassemble the original item.
That analogy perfectly illustrates the computational burden of IPv4 fragmentation. In the legacy system, if a router received a packet that exceeded the maximum transmission unit, or MTU, of the next physical link.
Oh, say, moving from fiber to Wi-Fi.
For instance, a packet moving from a high-capacity fiber optic backbone onto a constrained wireless link, the router was forced to halt.
Pull out the box cutter.
It had to slice the packet's payload into smaller fragments, generate entirely new IPv4 headers for every single fragment, populate those 3 fragmentation fields to ensure they could be tracked, and transmit them.
And the destination host deals with the glue.
The destination host was burdened with holding all these fragments in a memory buffer, waiting for the final piece to arrive before attempting reassembly.
What if a piece gets lost?
If a single fragment was dropped due to network congestion, the entire assembly failed, and the source had to retransmit the entire massive payload.
That's terrible.
It wasted massive amounts of CPU and memory on core infrastructure routers.
So how does IPv6 handle a massive packet hitting a small link without those fields?
IPv6 introduces a strict rule. Core routers do not fragment packets. It is explicitly forbidden.
They just refuse.
If an IPv6 router receives a packet that exceeds the outbound link's MTU, it drops the packet immediately.
Just trashes it.
It drops it and then utilizes the Internet Control Message Protocol version 6, or ICMPv6, to generate a packet too big error message, sending it directly back to the original source.
Saying, hey, you fix this.
The responsibility for sizing packets correctly is shifted entirely to the endpoints. IPv6 relies on a mechanism called path MTU discovery.
Path MTU discovery.
Before a host initiates a massive data transfer, it sends probe packets to dynamically discover the smallest MTU limit across the entire path to the destination.
It checks the tunnel size before driving the truck in.
Beautifully said. It then meticulously sizes all its outbound packets to ensure they will smoothly transit every link without ever requiring a router to pull out a box cutter.
That is so much smarter.
If a host absolutely must send fragmented data, it handles the fragmentation itself before transmission, utilizing an extension header, keeping the core network blazing fast.
That accounts for 4 of the cut fields. The last casualty is the header checksum. Dropping the error checking at the IP layer feels a bit risky. Why remove the safety net?
The header checksum was a necessary safeguard in the 1970s and 80s when physical network cables were highly susceptible to electromagnetic interference and data corruption.
Crappy copper wires.
However, modern network architecture has evolved. The Layer 2 data link protocols like Gigabit Ethernet or modern Wi-Fi have highly robust frame check sequences built directly into the hardware to detect corruption.
So the physical layer checks it.
Furthermore, the Layer 4 transport protocols, specifically TCP and UDP, calculate their own complex checksums that cover both their payloads and a pseudo-header derived from the IP addresses.
So having the IP layer perform a checksum as well was just redundant busy work.
It was worse than redundant. It was a massive performance bottleneck. In IPv4, there is a field called time to live, or TTL, which prevents packets from looping infinitely. Every time a router processes a packet, it must subtract one from the TTL field.
Okay, simple math.
Because the TTL field is inside the IPv4 header, the header is technically modified at every single router hop. Therefore, the router was forced to completely recalculate the header checksum before forwarding the packet.
At every single router.
By stripping the checksum out of IPv6, designers freed core routers from performing millions of pointless mathematical calculations per second, vastly increasing overall throughput.
Here's where it gets really interesting. If the primary IPv6 header is a rigid, unchangeable 40 bytes, and all the variable options have been stripped out, how does the protocol handle exceptions?
Good question.
What happens if a packet actually requires specialized routing instructions or security parameters?
This is where the true elegance of the IPv6 architecture shines. It introduces the concept of extension headers.
Extension headers.
Instead of cramming optional data into the primary header, IPv6 utilizes a next header field within that 40-byte block. Think of the fixed IPv6 header as the incredibly powerful engine of a freight train.
Okay, I like this.
It always looks identical, and the switches on the tracks the routers wave it through at maximum speed. If the packet contains no special instructions, the next header field simply points to the TCP or UDP data payload, which acts as a single cargo car.
The engine pulls one car.
But if special handling is required, the sending host can attach specialized train cars directly behind the engine. These are the extension headers.
And you just daisy chain them together.
Exactly.
The engine points to the first extension car points to the second, and the final car points to the data payload.
Exactly. And the crucial efficiency game is that intermediate routers generally ignore these trailing cars. They read the 40-byte engine, determine the destination, and forward the entire train without inspecting the cargo.
What kind of specialized instructions are we talking about? The text mentions a few specific extension headers, starting with the hop-by-hop options header.
The hop-by-hop header is the singular exception to the rule we just discussed.
So routers do read this one.
If a hop-by-hop header is attached, it must be the very first train car behind the engine, because it contains instructions that absolutely must be processed by every single router along the delivery path.
Give me an example.
It is reserved for network infrastructure level commands. A fascinating implementation of this is the jumbogram.
The name jumbogram makes it sound like a giant piece of candy, but it's actually about pushing the physical limits of data transfer.
The standard IPv6 payload length field is only 16 bits long, which mathematically restricts a standard packet payload to roughly 64 kilobytes.
Which is fine for most things.
For the vast majority of internet traffic, this is perfectly adequate. However, in highly specialized environments like localized supercomputing clusters or massive data center storage fabrics, processing millions of 64 kilobyte packets introduces unacceptable header overhead.
Too many envelopes, not enough letters.
The hop-by-hop extension header allows a host to declare a jumbogram payload, expanding the size limit to a staggering 4 gigabytes in a single packet.
A 4 GB packet.
Every router on that specialized path must read the hop-by-hop header to understand how to allocate memory for a packet of that magnitude.
The text also outlines a routing header, which functions like handing the packet a highly specific itinerary, dictating exact intermediate router stops it must make before arriving at its final destination.
A guided tour.
And we touched on the fragment header earlier. If the sending host realizes it absolutely must chop up a massive payload, it attaches a fragment header train car to each piece.
Right.
The intermediate routers don't care, they just route the pieces. Only the final destination host reads the fragment header to understand how to reassemble the puzzle.
It creates a beautiful separation of responsibilities. The core network is optimized exclusively for speed, while the complex logic of fragmentation, end-to-end security, and advanced routing is pushed to the intelligent edges of the network.
We need to transition to the sheer scale of this architecture. We've alluded to the 128-bit elephant in the room, addressing and auto-configuration.
The big numbers.
Let's look at the math. IPv4 uses 32 bits. IPv6 uses 128 bits. The total address space is 2 to the power of 128. That produces a number so large it requires new vocabulary, 340 undecillion.
To visualize a 340 followed by 36 zeros, Hagen's book provides a mind-bending analogy.
The grains of sand.
That amount of space is sufficient to assign multiple, globally unique IP addresses to every single grain of sand on the entire planet Earth.
Every single grain of sand.
If you assigned 1 million IPv6 addresses every microsecond, the sun would burn out and the solar system would collapse before you exhausted the address space.
So we're never running out.
The designers wanted an architectural ceiling so phenomenally high that humanity would never have to engineer another IP version upgrade due to scarcity.
But dealing with a number that massive creates a human interface problem.
Yes, typing it.
IPv4 notation was simple. 4 decimal blocks, like 192.168.1.1. IPv6 notation abandons decimals entirely for hexadecimal formatting, utilizing numbers 0 through 9 and letters A through F.
It looks a bit like alien code at first.
An address is written as 8 blocks of 4 hexadecimal characters, separated by colons. You end up with something that looks like 2001:00000000000000002:B3FF::FE1E::A329.
Quite a mouthful.
That is intimidating to look at, let alone type into a server configuration file.
The visual complexity is undeniable, which is why the protocol includes strict abbreviation rules to compress the notation.
How do you shrink it?
If an address contains a sequence of consecutive blocks comprised entirely of zeros, you can collapse that entire sequence into a single double colon.
Okay.
So that massive string you just read collapses into a much more manageable 2001:DB8::B3FF::FE1E::8329.
But the golden rule of the double colon is that you can only deploy it once within a single address.
Right. Only once.
If an address had 2 separate sequences of zeros, and you use the double colon twice, the computer parsing the address wouldn't know exactly how many blocks of zeros to expand in each location to successfully reconstruct the full 128-bit sequence.
It would be ambiguous.
It wouldn't know the layout.
That is a critical constraint. The compression must always allow for perfect, unambiguous decompression back to the binary reality.
Makes sense.
But while making the notation legible is helpful, the true revolutionary leap in managing this massive namespace isn't about how humans type the addresses.
It's about not typing them at all.
It is about removing humans from the process entirely. The killer feature of IPv6 is SLAAC, stateless address auto-configuration.
This is the feature that completely changes how networks are built. In the IPv4 world, connecting to a network requires a dedicated middleman.
The DHCP server.
When you plug a laptop into a switch, the laptop essentially broadcasts a plea for help. I need an IP address, a subnet mask, and a gateway.
A cry into the void.
A dedicated DHCP dynamic host configuration protocol server must hear that plea, consult its pool of available addresses, and lease one to the laptop.
Right.
If that DHCP server crashes or the pool is exhausted, no new devices can join the network.
IPv4 networking is inherently stateful and reliant on centralized administration. IPv6 introduces a paradigm where devices are entirely self-sufficient.
They handle it themselves.
When an IPv6-capable device powers on and connects to a link, it utilizes ICMPv6 to transmit a router solicitation message.
Okay, what does that mean?
It is actively querying the local environment, asking, are there any IPv6 routers present, and what is the global network prefix for this specific location?
The local router hears the solicitation and responds with a router advertisement, essentially handing the device the first 64 bits of the address, the network prefix.
In neighborhood it's in.
But how does the device figure out the remaining 64 bits without a DHCP server handing it out?
The device generates the second half of the address itself.
Just makes it up.
It takes the 64-bit network prefix provided by the router, and it mathematically combines it with a 64-bit interface ID that it generates based on its own hardware.
From its own parts.
By fusing the local network prefix with its unique hardware identifier, the device instantly synthesizes its own valid, globally routable 128-bit IPv6 address.
That's brilliant.
To be absolutely certain, it performs a quick process called duplicate address detection, essentially whispering on the local network to ensure no other device randomly generated the exact same suffix, which is a statistical near impossibility, and then it begins communicating.
The centralized DHCP server is completely eliminated from the critical path of basic connectivity.
Gone.
Consider the implications of this for you, the listener. Imagine purchasing a suite of smart home devices, a thermostat, a security camera, a networked appliance.
Typical Tuesday.
In the legacy IPv4 setup, your home router is burdened with running a miniature DHCP server, managing lease times, and potentially running into IP conflicts, or requiring complex port forwarding rules just to make the devices accessible.
A lot of friction.
With IPv6 autoconfiguration, you plug the device into the wall, it queries the router for the neighborhood prefix, calculates its own unique identity, and is instantly and directly accessible on the global internet.
It is true. Frictionless plug-and-play for an ecosystem of trillions of sensors.
If we connect this to the bigger picture, the architects of IPv6 realized they had to rethink how devices discover each other.
They did.
In IPv4, discovering services often relies on the broadcast address. A broadcast packet is essentially a network-wide shout.
Exactly.
It is blasted to every single interface on the subnet. Every computer, every printer, every mobile phone is forced to interrupt its CPU cycle, open the broadcast packet, process the request, and determine if it is the intended recipient.
It's exhausting for the network.
In massive environments, this constant shouting creates network storms that severely degrade performance.
It's the equivalent of someone walking into a massive, crowded restaurant with a megaphone just to ask if anyone found a set of car keys.
Everyone has to stop eating to listen.
The IPv6 architecture fundamentally eradicates the concept of broadcasting. There is no broadcast address in IPv6.
Not at all.
Instead, it relies on highly refined multicast and anycast implementations.
Multicast.
Multicast functions like a targeted radio frequency. Devices explicitly tune in to specific multicast groups. When a router needs to advertise its presence, it doesn't shout at everyone. It sends a single multicast packet addressed only to the group of devices that are actively listening for a router advertisement.
So if you aren't listening, you don't hear it.
Devices that haven't joined that group simply ignore the packet at the hardware level, saving massive amounts of processing power.
And Anycast operates on an entirely different logic.
Anycast is a brilliant routing concept. It allows network administrators to assign the exact same IPv6 address to multiple geographically dispersed servers.
The same address for different servers.
Yes. When a user sends a request to an Anycast address, the Border Gateway Protocol routing infrastructure analyzes the network topology and automatically delivers that packet to the single server that is topologically closest or most optimal.
That sounds like magic.
It is a foundational tool for load balancing and global content delivery networks. You could deploy identical DNS servers in Tokyo, London, and New York, all sharing a single Anycast IPv6 address.
But everyone types the same address?
The network geometry inherently guarantees that a user in Paris is routed to the London server, while a user in Kyoto hits the Tokyo server, minimizing latency without complex geographical load balancers.
Let's transition into the actual anatomy of these addresses, because understanding how they are built leads directly into a critical debate regarding digital privacy.
A huge debate.
Login breaks down the structure of a standard global unicast address, the type of address your devices use to navigate the public internet. These typically begin with a binary prefix 001. A standard internet service provider will generally assign a home or a corporate site a /48 prefix.
That 48.
Can we dissect what that 48 allocation actually provides to the end user?
When an ISP delegates a 48 prefix, they are locking in the first 48 bits of your 128-bit address. Those 48 bits represent your specific geographical or corporate site.
Your digital zip code.
Subtracting 48 from 128 leaves you with 80 bits of unallocated space to manage your internal network. The architecture designates the next 16 bits specifically for internal subnetting.
Okay, 16 bits.
Utilizing 16 bits gives the network administrator 65,536 distinct internal subnets to deploy.
65,000 subnet.
You could assign a dedicated, globally routable subnet to every single room in a massive corporate skyscraper and barely make a dent in the allocation.
It's an almost absurd volume of localized space. Once you define the 48 site prefix in the 16-bit subnet, you are left with the final 64 bits.
The interface ID.
This is the interface ID we discussed during the auto-configuration segment. The text details a highly specific bit manipulation process called the EUI64 format, which the device utilizes to transform its physical MC address into this 64-bit interface ID.
It's a clever mathematical trick.
How does that mathematical transformation actually work?
It requires an understanding of hardware identifiers. Every network interface card possesses a media access control or MAC address burned into its silicon at the factory.
The permanent ID.
A standard MAC address is exactly 48 bits long, consisting of a 24-bit organizationally unique identifier assigned to the manufacturer by the IEE, and a 24-bit device-specific serial number.
So manufacturer and serial number.
To generate the 64-bit IPv6 interface ID, the operating system takes that 48-bit MAC address and violently splits it exactly in half.
Just chops it in half.
It takes the manufacturer half and the serial number half, pushes them apart, and physically inserts a fixed 16-bit hexadecimal value FFFE directly into the center gap.
Just shoves it in there.
This padding successfully expands the 48-bit number into a 64-bit number.
But the EUI64 standard dictates one additional, highly specific step regarding the binary bits themselves.
The final step involves inspecting the very first byte of the original MSC address. The operating system looks at the binary representation of that byte, isolates the 7th bit from the left, which the IE designates as the universal local bit, and flips its state.
Flips it from a 0 to a 1 or 1 to a 0.
If the bit is a 0, it becomes a 1. This mathematical inversion serves as a flag to the network protocol, explicitly signifying that this resulting 64-bit interface ID was algorithmically generated using the EUI64 format based on a universally unique hardware address.
I was reading through this process, and a massive red flag immediately jumped out regarding privacy.
You aren't the only one.
If my globally routable IPv6 address is constructed by permanently embedding my physical hardware's MC address into the final 64 bits, doesn't that create a permanent globally visible tracking identifier?
Yes, it absolutely does.
If I take my laptop from my home Wi-Fi network to a public coffee shop, come into an airport lounge, the first 64 bits the network prefix will change as I move between ISPs.
Because your location changes.
But that EUI64 suffix derived from my hardware will remain completely static. Could an advertising network or surveillance entity simply track that static 64-bit suffix as it roams across the internet, mapping my physical movements with terrifying precision?
That exact scenario terrified privacy advocates during the early standardization phases of IPv6.
I bet.
The EUI64 format essentially created a permanent supercookie baked into the very network packets themselves, trivializing global hardware tracking.
It's a privacy nightmare.
Recognizing the severity of this architectural flaw, the IETF developed and ratified a dedicated solution, RFC 3041, commonly known as the privacy extensions.
How did the privacy extensions neutralize the hardware tracking while maintaining the ability to auto-configure?
RFC 3041 modifies the behavior of the operating system. When a modern device connects to a network, it may still calculate its EUI64 address based on its MAC address, which is useful if the device is acting as a stable server that needs to receive incoming connections.
Okay, so servers keep the static ID.
However, for outbound communications, when you launch a web browser to stream a video or access a news site, the operating system executes a cryptographic algorithm to generate a completely random, mathematically opaque 64-bit interface ID.
A random mask.
It appends this randomized suffix to the local network prefix to create a temporary IPv6 address. All outbound web traffic is routed through this randomized address.
And it changes.
Furthermore, the operating system continuously rotates this random identifier over time, typically generating a new one every few hours or days.
So from the perspective of a data broker or a web server logging traffic, my IP address looks entirely different on Tuesday than it did on Monday, even if I haven't physically moved from my desk.
Exactly.
It severs the link between the hardware identifier and the network traffic.
It brilliantly preserves the user anonymity that we somewhat accidentally acquired in the IPv4 NAT environment, while fully retaining the architectural superiority of end-to-end globally routable connections.
Best of both worlds.
Modern operating systems across the board, including Windows, macOS, Android, and iOS, enforce these privacy extensions by default, ensuring the massive address space doesn't become a surveillance tool.
Beyond these global public addresses, Hagen's text outlines several classes of highly specialized local addresses that make internal networking incredibly fluid.
The private side of things.
I was fascinated by the mechanics of link local addresses, which are defined by the FE80 prefix. The text provides a theoretical scenario involving a conference room that beautifully illustrates the power of IPv6.
A link local address is exactly what the name implies. An address that is functionally valid only on the specific physical or logical link the device is currently attached to.
So it can't leave the room.
A core rule of IPv6 routing is that a router will never, under any circumstances, forward a packet destined for an FE80 link local address across a network boundary.
It's totally walled off.
The architectural magic of IPv6 is that every single network interface is mandated to automatically generate a link local address the absolute millisecond it receives power, regardless of whether a router or a DHCP server is present on the wire.
So going back to the conference room scenario, imagine you and a colleague enter a room with 2 laptops. The facility has no Wi-Fi infrastructure, and there are no network switches.
Just a table.
You simply take a standard Ethernet cable and plug it directly into both laptops. In the legacy IPv4 paradigm, that act initiates a frustrating troubleshooting session.
Oh, absolutely.
You have to open the network adapter settings, manually configure static IP addresses, ensuring they reside in the same subnet, manually configure the subnet masks, and then cross your fingers that the operating system firewalls recognize the connection. It's an administrative hurdle just to transfer a file.
In IPv6 paradigm, the instant the copper pins in that Ethernet cable make contact, the network adapters activate. Both laptops immediately take the FE80 prefix, run their MASA addresses through the EUI64 algorithm, and generate their link local addresses.
Instantly.
They then utilize the neighbor discovery protocol operating over highly efficient multicast to essentially introduce themselves to each other across the wire.
Handshakes all around.
Within milliseconds of physical connection, without a single manual configuration step, without any routing infrastructure, you have a fully functional, peer-to-peer network capable of high-speed file transfers and secure communication. It is pure, organic networking.
It feels like magic compared to legacy protocols. And alongside link local, the text discusses unique local addresses, or ULAs, which utilize the FC00 or FD00 prefixes. These replace the older, deprecated concept of site local addresses.
Unique local addresses serve a critical function for enterprise architecture. A ULA is a globally unique address generated using a pseudo-random algorithm to ensure statistical uniqueness, but it is explicitly classified as non-routable on the public global internet.
So it's private.
They are the IPv6 equivalent of the private RFC 1918 addresses we discussed earlier, like the 10. Network. A corporation can deploy an expansive internal architecture managing factory floor robotics, secure file servers, and internal intranet portals entirely on unique local addresses.
Fully secure.
They remain perfectly secure behind the corporate firewall, mathematically unreachable from outside threat actors. But crucially, because the ULA prefixes are randomly generated rather than universally defaulting to the same 10. Block, if that corporation merges with another enterprise, their ULA spaces will not overlap.
Solving the merger nightmare.
They can establish direct VPN routing between the two sites without ever having to implement the nightmare of double NAT translation.
This brings us to the final and perhaps most practical challenge. If the IPv6 architecture is vastly superior, how do we actually cross the chasm from the old world to the new?
The million-dollar question.
We noted earlier that there is no mandated global cutover date. Hagen's text dedicates significant space to transition mechanisms. These are the engineering bridges designed to connect isolated islands of IPv6 adoption across the vast legacy ocean of the IPv4 internet.
The tunneling protocols.
The major mechanisms discussed are 6 to 4, ISATAP, and Teredo. Conceptually, how do these transition protocols actually function?
At their core, these transition mechanisms rely on a concept called encapsulation or tunneling. Imagine you have a highly advanced modern IPv6 corporate network in New York and another identical IPv6 network in London.
Okay, two modern islands.
However, the only network path connecting them is a legacy IPv4 backbone provided by an ISP that hasn't upgraded. The two IPv6 islands cannot speak directly.
They speak different languages.
A tunneling protocol solves this by taking the pristine, highly efficient 40-byte IPv6 packet and physically burying it inside the payload section of a clunky legacy IPv4 packet.
It wears a disguise.
The IPv4 packet acts entirely as a delivery vehicle, a disguise. It traverses the legacy internet using standard IPv4 routing rules. When it reaches the boundary router of the London network, the router mathematically strips away the IPv4 disguise, extracts the pristine IPv6 packet from inside, reads the 128-bit destination address, and routes it internally.
The text details the 6-to-4 protocol as one of the primary methods for this site-to-site tunneling. It utilizes a highly specific prefix, 2002::, to achieve this.
The brilliance of the 6-to-4 protocol is that it automates the creation of the IPv6 tunnel by mathematically embedding the site's public IPv4 address directly into the IPv6 prefix.
It fuses them together.
If a router possesses a public IPv4 address, it converts that 32-bit address into hexadecimal and inserts it directly after the 2002:: prefix. This instantly generates a massive, valid 48 IPv6 prefix that the router can use for its internal network.
Clever trick.
When an internal packet needs to reach another 6-to-4 site, the router inspects the destination IPv6 address, extracts the embedded IPv4 address of the remote site, wraps the packet in an IPv4 header, and fires it across the internet. It requires almost zero manual tunnel configuration.
Then there's ISATAP, the intra-site automatic tunnel addressing protocol, which is designed for internal corporate networks that have IPv6 capable servers, but are still running legacy IPv4 switches and routers between them.
Right, for internal upgrades.
But the mechanism that is arguably the most complex and critical for consumer adoption is Teredo. Teredo was specifically engineered to solve the most difficult transition problem: tunneling IPv6 traffic out from behind a stubborn legacy IPv4 NAT router that a user might have sitting in their living room.
Teredo is a masterpiece of network engineering workarounds. Standard IP and IP tunneling, like 6-to-4, often fails when it hits a home NAT router because the NAT device doesn't understand the protocol and simply drops the packet.
Because it's a weird packet type.
Teredo bypasses this by taking the IPv6 packet and encapsulating it inside a standard UDP user datagram protocol packet, specifically targeting port 3544.
Why UDP?
Legacy NAT routers are highly familiar with UDP traffic. It is the same protocol used for DNS queries and streaming media. The NAT router sees a standard UDP packet, happily translates it, and passes it out to the internet.
Sneaking it past the bouncer.
The Teredo infrastructure on the public internet then receives the UDP packet, extracts the IPv6 payload, and rats it. Teredo ensures that even if a user is trapped behind obsolete, restrictive home networking hardware, their operating system can still tunnel out and participate fully in the global IPv6 ecosystem.
These transition tunnels act as the invisible scaffolding, holding up the construction of the new internet while the legacy foundation is slowly decommissioned site by site, device by device.
They are temporary but absolutely vital bridges. They allowed the migration to happen organically, driven by demand and hardware life cycles, rather than requiring a globally synchronized high-risk infrastructure replacement.
We have journeyed through an incredible amount of technical architecture today. Synthesizing our deep dive into Silvia Hagen's IPv6 Essentials, the core takeaway is clear. IPv6 is not simply a larger parking lot built to accommodate more internet traffic.
Not at all.
It is a completely redesigned, highly optimized global highway system. It eliminates the fragile bottlenecks and security failures inherent to NAT. It introduces a streamlined, fixed-length header engineered for raw processing velocity.
It's built for speed.
It delivers a mathematically incomprehensible address space, 340 undecillion unique addresses, and backs it up with an elegant auto-configuration system, seamless mobility, and robust privacy extensions. It is the foundational requirement for making the Internet of Things a functional, secure reality rather than a chaotic network nightmare.
Understanding the mechanics of this transition isn't an exercise reserved for network architects. It is critical for anyone trying to grasp the parameters of our digital future. We are watching the rewiring of global communication in real time.
And that leads to a final, provocative thought for you to consider as we wrap up. We have explored how IPv6 restores the end-to-end connectivity model, eliminating the NAT receptionist and providing every single device from your vehicle to your thermostat with a globally unique, directly routable IP address.
True digital presence.
But if the technological walls of our home networks dissolve and our internal appliances are communicating directly on the global routing table without a middleman acting as a gatekeeper, what does that mean for our fundamental understanding of personal digital territory?
That is the big question.
If your home is no longer a localized walled garden, but rather a direct extension of the global public internet, how will we need to redefine the boundaries of our private lives in a fully organically connected IPv6 world?
It changes everything.
Think about the routing implications next time you plug a new smart device into the wall. Thank you for joining us on this deep dive into the architecture of the internet. Stay insanely curious, and we will catch you on the next one.